projective, fine projective, lambda modules. Right? So this. So this definition makes sense for any lambda. And so you can think of this. So this is the derived category. So I recall that it's constructed by taking the homotopic category of complexes of lambda modules and then inverting quasi-isomorphisms. So if you have a complex, a bounded complex of projective modules, then you can compute home in this derived category just as home in the homotopic category. So here I have the homotopic category of finite complexes, bounded complexes of finite projective modules. And in fact, the canonical arrow here is an equivalence of categories, right? So very explicitly, you can think of perfect complexes of lambda modules just as finite complexes of finite projective modules where morphisms are chain morphisms up to homotopy, right? So very good. And now we made a definition. So suppose we have main definition. So I recall that our goal is define the trace of an endomorphism of an object here. So suppose you have an object, a perfect complex, of lambda modules. And suppose you have its endomorphism in derived category. So F is endomorphism d lambda. So this is a full subcategory. So it doesn't matter whether I write here d lambda or d perf lambda. So it's a map from M to itself. Maybe I will change my notation. So let's call it P instead of M, because it's convenient for me to. So where P is Pi are finite projective. Define the trace of F on P to be the alternated sum of traces of Fi acting on Pi. So a comment on this first of all. So what is really written here? So I have a complex of bounded complex of finite projective modules. I have its endomorphism in the derived category. And by this equivalence, it's given by a chain endomorphism of this complex up to homotopy. So this F is a chain endomorphisms defined up to homotopy. So pi are finite projective. So we have the notion of trace of an endomorphism of a finite projective lambda module, right? And it's well defined as an element of this ring lambda bimol, which is referred to this as zero Hochschild homology, and that is lambda modulo its commutator, right? So you want trace of AB equal to trace of BA, and so you are forced to consider this quotient. So if lambda is non-commutative, then the trace lives here, not in lambda. So that is definition, but we have to prove. So we have to show that this is lemma, that trace is well defined. Okay, so let's see what do we have to check here. So first of all, suppose you have two endomorphisms. Let's see. So suppose I have F. It's endomorphism of P dot. And I also have F prime. And suppose that they're chain homotopy equivalent, meaning that F minus F prime is D commutator of D and H, graded commutator. So that's what it means, that it's chain homotopy equivalent, that they're chain homotopy equivalent, right? So we need to check that trace the sum of -1 to I of traces of Fi on Pi is the same as the same sum of traces Fi Pi. That's the first thing that we need to check. And let's do this. So, using the additivity of traces, if you have sum of two endomorphisms of a projective module, then the traces gets added. So it's enough to check that the trace of this, the alternated sum of traces of this guy is 0, right? So very good. So to this end, we write, so let's consider the trace of DH. So by definition, this is sum of traces of Pi itself, DH. So here D is a map. So I have Pi to -1 Pi. So this is D, and this is H. Right? So using the trace of DH is equal to trace of HD, we conclude that this is the same as sum over negative alternated sum of traces of Pi minus 1 of HD, right? Good. So And so this is equal to negative trace of HD. Right? Because the only difference is I have negative sign here because, well, it's clear. So because this discrepancy. So, and from this we conclude that the trace of HD plus DH is 0 in this quotient where the trace is defined. Okay? So this is one thing that we need to check. And another thing that we need to check is that this right-hand side does not depend on the choice of representative. It means that we can, so we have an object here, and it's possible that it's represented by two finite complexes of projective modules. So suppose you have P, and suppose you have, say, Q, and suppose we have phi, psi, and you have, so this is an isomorphism in this category. So which means that phi composed with psi is homotopy equivalent to the identity as well as psi composed with phi is homotopy equivalent to identity. Right? So, so here I have endomorphism F, and it gives me an endomorphism of this guy, G, which is, well, what is it? It's phi composed with F, composed with, что? Да, наоборот. F composed with phi. Good. So, so what we need to check is that the trace of F is equal to the trace of G, right? That's what we need. But, okay, so trace of G is the trace of F, well, so I substitute it here and I use the cyclic symmetry of the trace, right? If I put my phi here, so this is commutativity of the trace, right? So this is the same as the trace of F composed with psi composed with phi. And now this is homotopy equivalent to the identity. So that means that the whole composition is homotopy equivalent to F. And therefore, by what we already proved, this is trace of F. And this completes the proof. So for any object here satisfying some condition, right? It's a full subcategory. And in endomorphism, we have a well-defined notion of a trace. So, so in our application, lambda, well, first application, lambda will be z mod L to the power n z. And the complex that we are going to apply it to will be R gamma of a constructible sheaf of flat z mod L to the nz modules. So we want to show that it's perfect. And in order to do this, we need a criteria for perfectness, right? So, and so that is here is the criteria. So let's first make a definition. So let's say that a complex M so this is bounded from above complexes. It's a full subcategory consisting of complexes of lambda modules such that the homology of this complex vanish in sufficiently high degrees. So suppose I have M here, and we say that M has a finite toward dimension. If there exists a number n such that for every, say, k lambda module, this must be right lambda module. The tensor product, if I form the derived tensor product, okay, over lambda, right? That's why I need it to be right? This is a, oh, sorry, maybe. Let's put it this way. K tensor is L over lambda. Right? So this is the left module, this is the right, so I can take the tensor product. And what I want is that hi of this is 0 for I less than n. So a priori, so this tensor product, the derived tensor product is right exact. So it may, so M is bounded from above, so a priori it may have homology in all negative degrees. So the condition is that, in fact, this is uniformly bounded, so there exists n such that works for all k. So in particular, this implies that this is actually a bounded complex, right? I can take for M just lambda, and to get that homology of M supported only infinitely many degrees. But it's much stronger than it. So maybe to give an example, let's take lambda z mod L squared z, then M, which is just not a complex, a single object, z mod L. View it as a module here has infinite toward dimension.
What is R? There,
R means right. Right? So that is because if you compute Tor z mod Lz with itself over this ring, you'll get homology groups in all degrees, negative degrees. Да. Ну, как вы это считаете? Пишите такую резольвенту и умножаете ее на z по lz, и вы видите, что у вас получается комплекс с нулевым дифференциалом бесконечный. Good. So this is a strong condition. Now, and so here is a promised characterization. So lemma, assume that lambda is Noetherian. That means that every finitely generated left module, submodule of a finitely generated left module is also finitely generated. Here's our definition. Then the following two conditions are equivalent. Suppose you have a complex which is bounded from above. M is perfect. So it lives in this subcategory. If and only if two conditions hold. So M has finite Tor dimension. Well, and homology of M, which we know now is supported in finitely many degrees, are finite. Finite lambda modules. Finite here means finitely generated. So proof. So clearly these two conditions are necessary, right? So this implication is obvious. Well, so if you have a complex supported infinitely, a bounded complex of finite projective modules, homology also finite because lambda is Noetherian, and we have finite Tor dimension because when you compute the derived tensor product, if M is a complex of projective modules, you just compute it termwise. You take the tensor product termwise. Mi is flat. Projective module is in particular flat. It's a direct summand of a free module. So literally, so if M is a bounded complex of projective modules, say it's supported in degrees from negative n to positive n, then this tensor product is also supported in degrees from negative n to positive n. Он лежит в d минус. Это означает, что он как бы... Нет, ну что означает, допустим, что у нас m совершенно. Это означает, что m — это просто конечный комплекс конечных проективных модулей. Ага. Very good. So now we prove in non-trivial direction. So so first of all, so suppose you have a bounded complex, bounded from above, m negative one, mn. Let's see, like here. Negative m. So first, I can replace it by a complex of finite projective modules bounded from above. How we can do this? Well, so this is my M. Replace M by complex of the following type. P0, where Pi are finite projective. Well, any complex is quasi-isomorphic. Any complex which is bounded from above is quasi-isomorphic to a complex of projective modules. I have enough projectives. And if homology of these guys are finite, then I can choose for this resolution, well, I can assume that my this complex of projective modules is formed by finite projective, right? So for example, if M is supported just in 1 degree, so what you do, it's finitely generated, so you can take for P0 even a finite free module, then the kernel is again finitely generated because lambda is Noetherian, and you can cover it by a finite free module. You can even construct a free resolution, a finite free resolution. Well, resolution by finite free modules. Okay? So the only problem here, right? So I want to show perfectness of M, right? So I need to show that I can choose a resolution which is bounded from below. Okay. So let's look at this definition. So M is acyclic in O degrees less than this n, right? Because I can take for k lambda. So that means that this complex is also acyclic in O degrees less than n. So that means that I can take my P is quasi-isomorphic to the following complex. I have Pm, and I take Pn, and I take this infinite complex and I truncate it in degree n. So I take this quotient by the image of the differential. I know that, this truncation has the same homology as this complex in all degrees greater or equal than n by definition. And homology in degrees less than n, well, they're equal to 0 by assumption. So now the claim, which is really the key, is that Pn modulo the image of the differential is projective. Well, I will first show that it's flat. So again, so our M is quasi-isomorphic to this complex of finite modules where all terms are projective, except maybe for this last one. And they also have this n is chosen from the finite third dimension condition. So, okay. So what can we do now? We'll look at the exact triangle. So this is my P, or maybe, well, I can, it's quasi-isomorphic to M anyway. So, so M is quasi-isomorphic to this complex, and I will consider the following subcomplex here. So this maps to P n model the image of the differential, right? Every complex, for example, this one, maps to complex supported in 1 degree, namely just for this guy. It's supported in degree n. So I need to put it n here, right? Let's see. Right, in degree n. And the quotient, well, look at the triangle. So it will be the following complex, Pn plus 1, Pm. You just take, again, this complex and you, it fits into a short exact sequence of complexes. This is a subcomplex, and this is the quotient. So this is exact triangle, or distinguished triangle. So now I tensor it in the derived category with K, and I still get exact triangle. Да, это образ, это образ. Да. Ага, спасибо.
Как мы взяли отличные треугольники, все M и P, они же были по построению просто квазиизоморфные?
Ну, точные треугольники в триангулированной категории, они как бы, это то, что квазиизоморфно коротким точным последовательностям комплексов. Если хотите, ну, напишите здесь.
Да, это было одно и то же просто P и M. Они были просто квазиизоморфны, там не было ни ядра, ни P.
Нет, ну, в смысле, что...
Вы написали, что P ядро это один объект.
Нет, ну, хорошо, напишите, да пусть M это вот этот вот комплекс. Вот этот. Давайте я его обозначу как-нибудь. Это он называется каноническое обрезание степени больше или равной n. Он квазиизоморфен вот этому. Вот я его здесь и поставлю, если хотите. Это то же самое. Может быть, это... Угу. Теперь лучше?
Просто первый объект бросили, да?
Да. Угу. Это называется как бы глупая фильтрация. Вот то, что вот здесь написано, а это каноническое. Good. So, and I also need to tensor this with K. Now, let's, so what do we want to show? We want to show that this torus, so we want, well, I will write, so tor I lambda K and Pn over model the image of D, these all torrs are equal to 0 when I is greater than 0. So I claim that this this exact triangle gives me this. Let's see why. So let's, for example, prove that tor 1. So what you're supposed to do, you take this triangle and you write long exact sequence of cohomology groups. So let's start with h n minus 1. Hope I haven't confused anything. Let's see. Yeah, so no, I did confuse. So this complex, this guy, I want it to sit in cohomological degree n. So this must be put in cohomological degree n. That means that I need to shift it by negative n, right? Remember that shifting by 1 is shifting to the left. Okay? So, for example, tor 1 is of k and this Pn, model of the image of D, is by definition Hn of this tensor product. Pn image of D. Twisted by negative. Right? Okay? So now, yeah. That's because I have the shift. So what do I have here? So in this long exact sequence, we have Hn minus 1 of k tensored with tau less or equal than np. And here I have Hn of k tensored with, need more room. So I'll write it here. So this will be Hn of the following complex. I need to take this tensor product. But all these guys are projective. So when computing the tensor product, I can do it termwise. So this will be Pn plus 1 tensor k. K tensor Pn plus 1. K tensor Pn. So now this is 0 because the complex has no term. The degree 0 term of this complex is 0. Now this is 0 because the complex here is k tensored with m, right? This complex is quasi-isomorphic to m, and n minus 1 is less than n. So you see that the group that we are interested in is kind of sits in between two zeros in this one exact sequence. And therefore, it's 0. Right? So, and clearly the same argument, if I replace n by minus 2, it also works for the same reason. Very good. Now I can erase this. So, so we proved that.
Не соображу, а разве вот P-фактор, если взять модуль свой, P-фактор по образу,
Да.
для него не можешь сам комплекс, свою старую резольвенту, использовать как резольвент?
Ну, я могу, и что? И как? Но она будет бесконечная.
Но у нее же нету когомологии. Ну, значит, у нее тары нулевые.
В смысле, сейчас. Сейчас. То есть, нет. То есть я возьму Pn, фактор по образу. Дальше тут Pn. Pn плюс 1. Ну, это резольвента. Ну хорошо, я ее тензором умножаю на k, и что? Ну да, можно это было иначе сказать, действительно, как Володя говорит. Можно взять такую вот, чтобы вот это доказать, можно было бы поступить так. Вот взять вот такую резольвенту, n плюс 2, и ее умножить на k. Значит, просто использовать ее. Минус 1 и так далее. И что мне надо доказать? Мне надо проверить зануление вот это. То есть мне надо проверить, что этот комплекс ацикличен во всех местах, кроме нулевого. Но что я знаю? Я знаю, что если я возьму тензорное произведение K и M и посчитаю когомологии, то они все будут нулевые в степенях меньших n. Но m — это такая вот бесконечная штука. Вот m. Это просто как бы часть комплекса, которая вычисляет вот эти тензорные, вот эти когомологии. Они равны нулю. Хорошо? Другое доказательство. Ну, в сущности, то же самое доказательство. Very good. Okay, so now, so we know that it's flat, and now I will use the following fact. So fact if lambda is Noetherian, say V is finite lambda module, then V is projective if and only if it's flat. Right? So that means that Pn model of the image is projective. And the lemma is proven. Right? We replaced M by a finite complex of finite projective modules. Good. Now here is an application. Theorem. Suppose I have constructible flat z mod L to the nz sheaf on a curve C over an algebraically closed field. Then it's R gamma of C. Well, I will separate this. Okay, it's R gamma of C with coefficients in F. And also R gamma with compact support. And I recall what this is. So you take your curve C, you embed it into something a projective curve, you call it J, and this is defined to be R gamma of C bar J or chic of F. So these guys are perfect. Well.
Here C is the curve, or C can be any variety?
It can be any variety, right. It can be any variety, but I need it for curves. Yes. Any compactifiable. So finite type. Separated. So Z mod L to the nz. So proof. So clearly, this guy is flat because its stalks at the points which are not in C are all zeros. So it's enough to prove for gamma. And what you use is the base change. The universal coefficient formula. So C F tensored with any k is the same as R gamma C F. Well, I don't need the derived tensor product here. I just put it because F is flat. So, this is the universal coefficient formula, and now we know that H I of R gamma C with coefficient in F tensor with K. Well, this is a sheaf. So it's homology zeros when I is less than 0, right? Pretty simple. So very good. So what we get from this, so though the kind of separated, well, the homology groups of F need not be perfect modulus over Z mod L to the nz, the complex, the entire complex is perfect.
Why is it bounded from above? So if we take R gamma, we take it in general.
Well, we proved that homology of any sheaf on a curve vanish in degrees greater than 2.
So you take injective resolution and then you truncate it as
No.
that's your first step.
No. I mean, well, I know that this this complex has homology only in degree 0, 1, and 2. We proved it for any sheaf. Yeah, maybe very important. So characteristic of K is not equal to L. Otherwise, this homology are not finite. Maybe all we do under these assumptions. Good. So, what we achieved? At least now we can formulate the Laffert's trace formula with finite coefficients. That was our goal, because then we can hope to reduce the general case to the case of trivial sheaf, constant sheaf, by passing to a cover of my curve. So the theorem that we want to prove is the following. Well, again, C0 will be a curve over a finite field. C is its base change to algebraic closure. I have F0 constructible flat Z mod L to the n Z sheaf on C0. I will denote by F its pullback to C, and it comes together with the wave structure. Right, because it's pullback. This is on C. And then the formula assures that the alternated sum of, well, the sum of traces of Frobenius, so this is over all k points of C0, acting on the fibers. Fibers are flat, so that means that they're free actually. And this sum is equal to the trace of Frobenius acting not on the homology group, which doesn't make sense, but on R gamma itself. That's the only thing that makes sense, of C with coefficients in F. Okay? Now, so we want to prove this. And so I want to reduce the proof. I want to reduce the proof to the case when F is a local system, and then use some Galois covers to realize this local system. And in order to do this, I want to show that the both hand side are additive in short exact sequences. So additivity here is obvious. I need to check additivity here. So good. So proposition. So suppose I have, let's see, how I want to write it. Yeah, so F 0, 0, F 0, 1, F 0, 2. So short exact. And F0i are flat. And then what we want to prove is that alternated sum of traces, trace of the Frobenius, acting on R gamma CFI, that this is 0, right? Trace here plus trace here is equal to the trace here. Let's try to prove this. So, well, I have a short exact sequence of sheaves. If I apply this, this is a triangulated functor. So that means that it gives rise to an exact, to a distinguished triangle, R gamma C. Да, ну нет, ну как, это pullback их на C. Ага. Okay. So this is a distinguished triangle. And now this is, this has Frobenius, this has Frobenius, and this has Frobenius, and everything commute. So, and what we want to show is that the trace here is equal to the sum of the traces. So, to achieve this, we might want to prove a more general statement on matrices. Okay, so what would be the more general statement? So, okay, so suppose you have M0, M1, M2. This is a triangle, distinguish triangle in G-perf. Well, I could put some lambda here. And you have phi 0, phi 1 acting here, and phi 2. And this maps commute, right? So the section commute. So if I say if alpha, if I take alpha of phi 0, this is the same as phi 1 alpha, and also here, then trace of phi 2 of phi 1 is equal to the trace of phi 0 plus trace of phi 2. Well, so you can try to prove this, but it's kind of boring because the statement is false. And let me give you an example. Why? So let's take the following complexes. So I take for lambda z mod L squared z. And my first complex will be 0 z mod L squared. So this will be actually complexes of finite projective modules. The second complex will be z mod L squared z. And this is z mod L squared. This will be multiplication by L. And this, so this is 0, this is M1, and M2 will be Z mod A squared. And this is 0, and the map, well, so this is identity, and this is identity. Right? So, and I claim that it commutes. Well, what do you need to check here? You need to check that, is there anything to check? No, nothing. Okay, so now I need to define this phi0, phi1, and phi2. And so this will be phi0, and I take it to be 0. Now, okay. So here I also take it. This is phi2, and it will be also 0. And this will be also 0. Very nice. And here, well, I need something non-zero, right? So let's put L here, multiplication by L. And I claim that that's a commutative diagram. Well, it's commutative diagram in derived category, right? So, of course, if you you see this map, this identity map does not commute with this, here it's multiplication by L, here it's 0. So it doesn't literally commute. So let's call this map, this is going to be, what alpha, and this is going to be beta. So, well, what do we want to check is that phi1 composed with alpha is equal to phi1, no, this way, with alpha, is equal to phi2, so, sorry, maybe I think it was correct. Okay, I want to check that this is phi2 composed with beta, right? So it's not true just in the category of chain complexes, right? This doesn't commute with phi I. But I claim that these two maps are homotopic. So that means that if I take the difference of these two chain maps, then it's homotopy equivalent to 0, and I define this homotopy, well, this map H, and it will be identity, right? And it's 0 everywhere else. I claim that this is the commutator dH plus HD, right? So that means that in the derived category, this is equal to this. So the assumptions of the lemma are satisfied. So, but clearly the trace here, well, so trace here is what? Is here is 0, so it's just L, right? So this is false. Okay? So we have to do something. And, well, surprisingly, all you have to do is to reformulate this lemma a little bit. And then it holds in that generality. So And I need a digression. So as you see, the problem is that this commutativity in the derived category is a very weak condition, right? And that's why triangulated categories are not that good. But somehow there is a general philosophy that, so if you have an abelian category, well, triangulated, its derived category itself is not, forgets too much information. So there is something called DG category or infinity category. There is another kind of approach to this who knows? Yes. This is R gamma with compact support of F2. I use that notation. So these are perfect. It follows that this guy is also perfect. And now, so this has endomorphism, F. A filtered endomorphism. And it's, well, the trace of this endomorphism on this guy, which is the same as the usual trace, on F1, is equal to the sum of these two traces. And we get the proposition. OK, let's stop.